Okay, so welcome to week 9 of Electromagnetics in Guided and Wireless Media course that is being offered on NPTEL. The course instructor is Professor Pradeep Kumar from IIT Kanpur, and I'm Shazam Bhatt. So this is basically an extra session. This is a 8-week course, but we are into week 9 with this extra session where we can take up the problems from each of the session, each of the week, and discuss them again so that you can at least have a feeling of how to approach a basic particular problem in this in electromagnetics. And essentially what we are going to do for this session, we are into week 9, which is basically an extra session. And what we are going to do for this session is to maybe brush up your concepts from week 1 going to week 8. So we won't be dealing with all of the concepts, but the main key concepts which will be sort of important from the conceptual understanding point of view, from the conceptual understanding point. So that's going to be necessary as you go down the line in this course. So what we are going to do is we're going to take up 1 to 2 questions from each of the weeks, depending upon how the time goes, from each of the week, and we are gonna solve them, we're gonna discuss them, and we're gonna do this for all the weeks that we have been through. Okay, so now what we are going to do is we are going to take certain sample problems. So if you remember in let's go to week first. Let's go to week first. In the week first, what you studied, so this is also a sort of a revision lecture. Obviously, not everything, it's not possible to cover everything, but there's some specific things which are really necessary. So in the week one, you studied about the basics of electromagnetics, the basics of electromagnetic waves. You studied about the characteristic length scales, characteristic length scales. That means essentially what happens if your length becomes of the order of length of the system becomes of the order of wavelength. If your length is much less than wavelength, if your length is much greater than wavelength. So essentially what you saw is that if you have a transmission line, something like this, you have a transmission line, and if the overall length of the transmission line approaches the approaches the order of wavelength, then basically you have the transmission line approach which you need to use. And what you do in the transmission line approach, you have to treat it as if they are the waves, electromagnetic waves flowing through the circuit. There is the outgoing wave, there is incoming waves. You need to talk about reflections, you need to talk about transmissions. So essentially, what you studied was the reflection coefficient, the transmission coefficient, which you denoted by as gamma. Okay, and so that is the essential part of this transmission line approach. And if you have length scale greater than wavelength, then you basically have the ray optics regime, where you no longer have to take into consideration the wave nature. You can just consider the incoming electromagnetic wave as it's like a ray of light basically that's coming and hitting the object. It's also getting reflected, and you can apply all of those Snell's laws, laws of refraction, laws of refraction, and all other laws for this particular domain. And for this particular domain, you have the lumped circuit regime. Lumped circuit regime, which I believe was not discussed in this course for till now. So most of the first week dealt with this particular scenario. And here you also talked about when in the transmission line approach, you talked about the intrinsic impedance, you talked about the characteristic impedance, you talked about basically the lossless transmission line, and all of those things were covered in week first. So essentially, if you remember, you had a let's say for example, let's say if we take an example of let's say you have a lossless transmission line with say the inductance is given by 1.5 microhenries per meter. All of these units are in per meter, remember, and the intrinsic impedance of the line is given as 70 ohms, and it's operated at a frequency of 5 gigahertz, and we need to find its phase constant. Basically, it's a propagation constant which we need to obtain. We know that this propagation constant is basically equivalent to omega square root of LC. Okay, and now what we need to basically find is we are given everything, we need to find this C. We know that the intrinsic impedance is square root of L over C for a lossless transmission line. Otherwise, there is that imaginary part of this in the numerator and denominator that you know. So essentially, solving this, you obtain C. If you solve this, you obtain the capacitance. You put the capacitance back into the equation, you're going to get the propagation constant. Now, what are the units of propagation constant? It's in radians per meter. It is the beta is it's same as k, the wave vector. Okay, so it's same as k, which is basically omega over c. Where this c is basically it's a small c, it's the speed of light. Speed of light. This c here is the capacitance, and the L is the inductance. Don't get confused and mix these everything. Okay, so this is about it. And what if you need to find, apart from it, what if you need to find the phase velocity? If you need to find the phase velocity at which the phase of the wave is basically changing. So this is not the exact velocity at which the information is basically being transmitted. So there is something called as group velocity, and then there is something called as phase velocity. Okay. And this is the velocity at which the phases are basically changing. When you have a waves moving like this, where you have the continuous wave packets moving in, because you don't have a single frequency in a system, you have sort of a multiple frequency, and when you have a multiple frequency, you consider a wave packet, which is basically consisting of multiple frequencies. A wave packet looks something like this, which has a multiple frequencies, and so this is the wave packet. And essentially these there is a phase changing event. So the propagation speed of these phases at which the phases are changing is basically the phase velocity, and the group velocity is actually the velocity at which this envelope is basically propagating. So that is basically the velocity at which the information is propagating. So this is the actual velocity at which the information propagates. And this phase velocity in some cases, you will notice if you do deal with certain cases, the phase velocity can go greater than speed of light also. But it doesn't mean you're breaking any rules. It's just not the velocity at which the information is propagating. Okay. And essentially this phase velocity, you can write it in terms of omega over propagation constant. Okay. So that is this velocity basically. It's basically the phase velocity. The speed which was in the denominator, it was like for the electromagnetic waves, it's in general it's basically the speed, not a speed of, it can be speed of light, it can be speed of sound. If you are dealing with an acoustic wave, you can write the propagation constant as omega over ca, where ca is the acoustic velocity or the speed of sound. If you're dealing with the electromagnetic wave, this is an electromagnetic wave, then this propagation constant is basically omega over speed of light, CL. whatever you call it. It's a CL, it's the speed of light. And now, if you want to compute the phase velocity, you can compute the phase velocity as omega, which is 2 omega is 2 pi into frequency divided by beta. You have everything, you just put into the equation, you find the phase velocity of this particular electromagnetic wave. Okay, and what if you are given all of these things and you need to obtain the reflection coefficient. You need to obtain the reflection coefficient. How can you do it? If you are given everything, let's say you are given a length of 2 meters, you are given a phase constant of pi by 8 radian per meter, which is essentially beta, and you are given characteristic impedance as 50 ohm, and load impedance ZL is given as 150 ohm, and you need to find basically gamma L, which is basically reflection coefficient. How can you find it? It can be found by simply ZL minus Z0 divided by ZL plus Z0, which is basically the load impedance minus the characteristic impedance. Okay, and if you find it, you get 150 minus 50 divided by 150 plus 50. You obtain 100 divided by 200, which is 1 by 2, so it's 0.5. So your reflection coefficient is 0.5. And what does it signify? It signifies that if the wave was coming like this with an, let's say, the amplitude of 100, let's say the wave was coming with an amplitude of 100 millivolts. Okay, so the reflected wave will have the amplitude of around 50 millivolts. That means 50% of the electromagnetic wave is getting reflected from the load. So it's not perfectly impedance matched. Okay, that is the exact scenario. And in the same question, if you are supposed to find the input impedance is the impedance you see from the, let's say, this is the transmission line, and this goes on. So this is the impedance you see from it here. So input impedance you can find by Z0 ZL plus JZ0 tan of beta times length divided by ZL minus JZ0 tan of beta times length. You are given everything. You are given the length, you are given ZL, you are given Z0. You can obtain this input impedance and you get it approximately 30 minus 40J, which is basically complex. So it's a complex. Obviously, we're talking about the reactances also. We're not only talking about the resistances. So this is the resistance part, this is the reactance part. Okay, so there are two. There is imaginary part and the real part in this particular system. Then if you on it, you need to find the voltage standing wave ratio. How can you obtain the voltage standing wave ratio? You can simply obtain the VSWR, which is basically the maximum of the voltage that occurs in the transmission line. You can find it as the 1 plus magnitude of reflection coefficient divided by 1 minus magnitude of reflection coefficient. Reflection coefficient is 0.5, so you get the voltage standing wave ratio to be 3. Okay, and essentially why you need to take the magnitude here, because this gamma L can also be negative. Okay, and that is really going to be important because the sign also tells you about a lot of information about the phases of this electromagnetic wave. If the let's say if you get a reflection coefficient of minus 0.5 instead of plus 0.5, it would essentially means a phase change also. Okay, but what happens basically if you have a electromagnetic wave coming in like this, and if it exactly goes like this, then that means there is no phase change, and that means the reflection coefficient will be positive. But if your electromagnetic wave comes in like this and it goes back in a phase changed fashion, you can see that the phases are flipped, then your reflection coefficient is going to be negative. That's why when you use these reflection coefficients in VSWR, it has to be a positive quantity. So you take the magnitude of the reflection coefficient, so that suppresses the negative part by itself. Okay, so this is about this particular thing. Now, what happens if you go to this was about what you did in week first. Now in week second, you talked about the similar things, but you were more concerned about the power dissipation also, how much power is basically dissipated in the transmission line. And you know that once you obtain the reflection coefficients and the transmission coefficients, it can give you the information about the dissipated power. Okay? And how you can find it? Let's say you need to find the power dissipated by the load, and you are given the reflection coefficients, or you are given the intrinsic load impedance, intrinsic impedance, and you are given the incident power. Let's say this is you are given these informations. Then essentially you need to find the load power dissipated by the load. So what you can do is that using this information, you can find the reflection coefficient first, obtain the reflection coefficient. Using the reflection coefficient, because it will be a complex number, so it is going to have a real part and it's going to have an imaginary part. Okay, you have to take basically the mod magnitude of reflection coefficient, which will be under root of real part of it, real part square plus imaginary part square. So this will be the magnitude of the reflection coefficient. Okay, and then the transmitted power, the incident power to the transmitted power, you can write in terms of the reflection coefficient, or you can write the opposite. The transmitted power to the incident power can be written as 1 minus reflection coefficient square. So if you know the incident power, you can find the transmitted power, and you can also find the power dissipated by the load. So that is the essential thing. And now if you have two transmission lines that are connected. So let's say you have a one transmission line here, and it's connected to another transmission line, and it's really important. Such type of questions can be asked in several examinations even. And let's say you are given the first let's say this first transmission line is 12 meters. It was one of the questions also in the assignments, and this transmission line is around 10 meters. So the losses here are 0.20 decibels per meter, and the losses here are 0.30 decibels per meter. And at the intersection, the reflection coefficient is essentially 0.30. So essentially the waves which are coming here, they will be also reflected by the intersection. So there will be reflections at the intersection. Okay, so we need to find the total loss. So we need to find the total loss in combination because of the first transmission line, because of the second transmission line, and then because of this interface, which is basically between the two transmission lines. How are you going to find it? Essentially, you're going to find it. The loss here is given. It's given here also. So we need to find the loss at the intersection. So loss at the intersection in decibels can be obtained by in a logarithmic scale as 10 log to the base 10, 1 divided by 1 minus gamma square. Okay, and where does this 1 divided by 1 minus gamma square comes from? It again comes from this particular thing. It's basically incident power divided by the transmitted power. So that will be the loss. So how much it's incident and how much it's transmitted. That is essentially giving you the picture scenario of the loss. How much is basically lost. And now let me just make it full screen. Oh, okay, somehow. Okay, so there was some issue with this, and I hope it's visible now. Okay, so there was some issue with the recording, so now it's solved. So what you are given essentially is everything. You can find the losses due to the intersection. So this is because of the intersection. point where you are joining the two transmission lines. And essentially, what you now have is basically, let's, so what you now have is you can find the overall loss, which will be basically given by, just a moment, which will be given by this loss plus this loss plus this loss. But one thing that you need to consider here is the important thing, that is this is in decibel per meter, this is in decibel per meter, so you need to multiply it with the length. So when you compute the total loss, that will be 0.20 decibel per meter multiplied by its length, which is 10 meters, so that the meter and meter will go, everything will be in decibels. Similarly, plus 0.30 decibel per meter multiplied with its length, which is how much is it? 12 meters, plus then it will be 0. Plus the this particular loss. Okay, whatever the number will be. So this will be the total loss. So that everything comes out to be in decibels. You need to make sure that you don't obtain it in decibel per meter. You just multiply it with the length scale so that the overall power comes out to be in decibels. That is the essential concept in this microwave. And you will see this decibel per meter losses in also certain devices, like when you talk about high electron mobility transistors, which are essentially the microwave devices. These are the microwave high frequency devices, high frequency devices. So these are the transistors, but they are sort of having the high electron mobility, so that the the unity gain, or the transit frequency, or the transit time rather, is huge, so that the frequency at which it's working is enormous. So this high electron mobility transistor, it's made up of aluminum gallium nitride, and then there is gallium nitride basically, and you make a heterostructure from this heterostructure. And what basically happens, you have aluminum gallium nitride. It has a band gap of around 4 electron volt, 4 electron volt, and then you have a this is aluminum gallium nitride. It has a band gap of around 4 electron volt. Then you have a gallium nitride. It has a band gap of around 3.4 electron volt. And what basically happens is that when you combine these two in such a way that there is no there is no other spacer, a system, or a material in between, it forms a system which exactly looks something like this. Or in case most of the time in these devices you have another layer which is called as a which is an aluminum nitride layer, and then you have a gallium nitride layer. So aluminum nitride has a band gap of roughly 6 electron volts. So when you combine this system with a band gap of 4 electron volts, 6 electron volts, 3.4 electron volts, what basically happens, you get a system which looks something like this. So you have, so this will be a gallium nitride, this is aluminum nitride, so this is aluminum gallium nitride. Why I'm showing this is because I'm trying to explain these RF microwave devices, which are basically working in microwave frequencies. Microwave frequencies. And when we are talking about it, we are talking about in gigahertz. It can go even up to 50 gigahertz. It can go up to 100 gigahertz. Okay. And what essentially happens here is that at this particular position, you have the Fermi level crossing the conduction band of it. And this sort of forms like a it forms like a triangular potential for an electron. So this is like a triangular potential for the electron. And because of it, the electron's energy levels are confined here. So you no longer have a continuous energy, but you have a confined energy, and that gives rise to something called as electron wave function. And it looks something like this. This is called as two-dimensional electron gas. That means the electron is able to move in a two-dimensional fashion only, and it's confined in one direction. And that basically gives you a super high mobility, and it gives you a high frequency operation. Okay, and these devices work in microwave regions. And in these devices also, when you are talking about the characteristic losses, you also talk about in terms of decibel per meter, or you write it in terms of or you write it in terms of maybe watts per meter, whenever you are talking about the units. And in that, you have to also you have to again multiply it with the length scale of the transistor or the strip line, whatever you're using at the gate terminal in order to understand basic losses in these particular devices. So this is about it. Now, then, if we talk about what we did in week 3, in week 3, what we talked about was mainly the concept of lattice diagram. So what essentially was lattice diagram? It was a way to understand how the transmission line behaves and how the reflection takes place, how the transmission takes place. So let's say you had a transmission line like this. There was a voltage source, a steady state voltage source. There was a source impedance, and then was an intrinsic impedance. Then there was a load impedance, and essentially from the source side, when you launch a pulse of it or a voltage pulse, it's gonna go here because of the reflection. At this end, there will be reflection coefficient associated, which is ZL minus Z0 divided by ZL plus Z0. There will be reflection of the waves reaching the source again, and then there will be reflections from the source towards the load again, and the reflection coefficient from the source end will be Zs minus Z0 divided by Zs plus Z0. So you talk about the load reflection coefficient, source reflection coefficient, and then there is a time delay associated. For the wave to go from this to this end and then come back, it's going to take around twice the delay time. Okay, and from going to source to load, it takes TD, and then coming back, it takes TD, and it will be the overall time delay associated with it. And then you talk about a picture wherein you draw the length scale on this axis. So this is Z equals to 0 point, which is basically the source point. This is Z equals to L point. This is basically the load point. Okay. And then you draw the reduced or the normalized time here, which is time divided by the delay time. You have 1, 2, 3, 4, 5, and so on. So at this point, the time equals to 1 TD. So time equals to 2 TD, so on and so forth. So in 1 TD, the waveform basically reached the load end, and it reached up to a certain voltage value, let's say V1, and then it gets reflected and reaches the source end, and let's say it reaches up to a value of V2, then it again goes back, it comes back, and in 4TD it again reaches back to the source, but obviously with amplitude, let's say V3. And as you go on and on, you see that the V1 is greater than V2 is greater than V3 most of the times, because this voltage goes on reducing because of the successive reflections. It depends upon the reflection coefficient. Obviously, if the reflection coefficient is 1, that means all of the wave will be gone towards the source, and then it will again come back towards the load. So, but this is the essential idea. Then from this lattice diagram, you essentially draw the variation of load voltage with respect to the time, and then you draw a time scale on it. So this is basically a transient variation of the load voltage. So you have a 0, you have time TD, you have 2 TD, you have 3 TD, and you know that there'll be a there'll be no voltage in this time because it takes time TD to reach the voltage towards the load. So the voltage will start from TD, it will go on increasing, and then it will reach to a value, some value, maximum value. At 3 TD, it's again receiving some voltage from the source, then there will be some drop or can be increased depending upon how it will behave. So essentially you're talking about a transient system which is basically reaching its steady state value. And that is the essential part of it to understand the dynamics or the transient dynamics of the voltage in these particular transmission lines. So this was the essential concept of lattice diagram that we talked about. And we solved a couple of questions on it, how to basically approach these lattice diagram questions. And then you talked about what happens if you have an inductor load and what happens if you have a capacitor load and what sort of waveforms are we expecting, because what happens is you are talking about the incoming waves, and then you are talking about the outgoing waves. You're talking about essentially the phase shift at this point. So how much is the phase shift and how that is occurring obviously depends upon the reflection coefficient of the load. And then coming back from the source, so this is the source and this is the load end, and then we talk about the source reflection coefficient as well. Okay, so accordingly, let's say there's a pulse of waveform going towards the load end. If it flips in phase, it will look something like this and come back to the source. If there is a phase flip again at the source end, it will look back again like this, and it will hit, then it will come back, then it will come back here, then it will go back and forth. So accordingly, it's how these pulses of the voltage pulses behave with respect to it. Now you talk about if you had a different types of loads, let's say you had a capacitive load or an inductive load, then how essentially the voltage waveform is going to behave. So if you have an inductive load, most of the time the voltage waveform, how it is going to behave is that it will be flowing something, the voltage will be like this, and then there will be a sharp peak at this, there will be a spike. And this is mostly because of LdI by dt sort of kick because of the inductance. So the voltage of the inductance is LdI by dt because there's a di by dt term. So there will be a sudden spike in the voltage because of the inductance effect. And the capacitance, if there's a capacitive load, it will be in the opposite direction. There will be a voltage starting, and then there will be a spike, and then it will start to basically drop in this fashion. Okay, so this was about week 3, what you did or studied in week 3. Now moving into the week 4, the essential concepts that you, just give me a moment, that you studied, what was it related to? You went into the electromagnetics, and you talked about mostly electromagnetic waves. You talked about the Maxwell's equations. You talked about the electric fields, the magnetic fields, and you talked about the permittivity, permeability, and all other things. And also you talked about the electric field and magnetic field energy densities. So how much of the energy is basically associated with these electromagnetic fields? And the essential concept was something related to called as Poynting vector, which gives you the average, the density of electromagnetic energy flowing in the propagation direction, which you write as the average power in the electromagnetic field is half of real part of electric field component times the complex conjugate of the magnetic field. Okay, and essentially what you have is you have an electromagnetic wave, which is basically looks something like this. This is the magnetic field component, not drawn up to the scale, obviously. And you have a propagation direction like here. So this is the electric field component, this is the H component. So this is the Poynting vector will be pointing towards this particular H direction. Because you see, if the electric field is along, along Y, and your magnetic field is along X cap, then essentially E cross H is gonna give you basically Y cross H X, so it will be Z. So it's something like cyclic rule. So X cap, Y cross H is going to give you minus Z cap. So your electromagnetic wave propagation is going to be in minus Z direction, or it will be in Z direction depending upon the directions of the electric and magnetic fields accordingly. And then you talked about what will be the power stored. The power stored in electric field and magnetic field. In electric field, it's half of epsilon naught E is basically E square, but you can write it in terms of E into E conjugate. And then you can write magnetic field as 1 over 4 mu naught H conjugate. Okay, accordingly, you can find the the power density, and this is essentially the power density, and you will always have the units of something like joules per meter cube, joules per meter cube, and it's essentially not. I mean, you can have the joules or you can have a watt per meter cube if it's you are talking about the power, but joules is for the energy density. If you're talking about the energy density, and actually this is basically energy density. So this is the energy stored in the electric field and magnetic field. Then what we talked about? Then we talked about what basically happens if an electromagnetic wave. Then you essentially talked about certain polarizations. You talked about you talked about elliptical polarization, which is basically a general form of a polarization, and all other polarizations can be derived from it. So if you have an elliptically polarized wave, which looks something like this. So this is the major axis, this is the minor axis, and there can be left elliptically polarized and a right elliptically polarized wave. What does it depend upon? So this is something called as right elliptically polarized. If it looks something like this, that is left elliptically polarized. But if somehow these two shrink and it becomes a circle, so it becomes a circularly polarized wave. Okay, so essentially what you have then is a circularly polarized wave. And if it's rotating like this, it's called as left circular polarization. If it's rotating like this, it's called as right circular polarization. What is the rotation we are talking about? It's the direction of the motion in basically how basically these vectors are rotating. So let's take an example. If you have a if you have a magnetic field given as, let's say, minus y cap h naught cos of omega t plus x cap h1 sine of omega t. So essentially what you do is you plot omega t and you plot h of z. That means you give different phases to omega t and you plot it. For omega t, let's say equivalent to 0, you get h of z to be minus y h naught minus y cap h naught. For omega t to be pi by 2, you get it to be x cap h1. For omega t to be minus pi by 2, you get it minus x cap h1. For omega t to be pi, you get it y cap h naught. For omega t to be pi by 4, you get minus y cap h naught divided by root 2 plus x cap h1 divided by root 2. For omega t to be minus pi by 4, accordingly you will get the values. Now if you plot these values on a scale where this is y direction, this is x direction, and the z direction is going either in or out, we will see. Then what you do, you start with omega t equals to 0. Okay, so you have omega t equals to 0. At omega t equals to 0, the h of z is minus y h cap. So it is along this direction. So this is minus y cap h naught. At omega t, this is at omega t equals to 0. At omega t equals to pi by 2, which is basically omega t equals to pi by 2, your value is x h1. So this is x h1, x cap h1 in the x direction. Then accordingly, omega t equals to pi, the value is essentially y h naught. Similarly, at omega t equals to minus pi by 2, your value is minus x cap h1. And at omega t equals to pi by 4, which is along this direction, the vector is going to be like this, and the value is minus y cap h naught divided by root 2 plus x cap h1 divided by root 2. And this is going to form the major axis of the ellipse. And similarly for the opposite direction, it will be opposite. So it'll be the opposite value. And when you connect these points, what you're going to form is something like an ellipse. So that is basically what I was talking about. So you're going from this point to this point and you're forming the ellipse like this. Now in the opposite scenario, if you form an ellipse something like this, then will be basically called as left elliptically polarized, and the red one is basically right elliptically polarized. And if you have the uh, equation of the field in such a way that this forms like a circle, then this will be circularly polarized wave. Right circularly polarized in case you are going in this direction of the rotation, and left circularly polarized in case you are going in the opposite direction. So this is left circularly polarized. And another case is basically linearly polarized light. Linearly polarized is if this ellipse squeezes to a sort of a linear fashion, so that you have essentially a waveform that is basically varying like this only, either this or it can be this. Okay, so these will be essentially the linearly polarized waveforms. If your waveform is looking something like this, when you put in the phases and you plot it at with respect to each phase. Okay, so this was about polarization. Then you talked about how the electromagnetic wave interacts with the medium, interacts with the medium. So essentially what you talked about, that what happens to different field components. What happens to electric field? What happens to magnetic field when it starts to interact with the system? So let's, for example, you took a slab. So let's say this was a glass slab with some relative permittivity, with relative permeability as well. And the refractive index is basically square root of relative permittivity. It's actually square root of relative permittivity times the relative permeability. But most of the time we take this as to be equivalent to 1 because we are not considering magnetic materials. But I told you that if it's a magnetic material, let's say if it is some sort of a magnetic material having a significant magnetic response, then this mu r value will be high. I mean, it's going to increase. And your refractive index will depend on both epsilon r and mu r. So that is essential. That's why most of the time in here, we took the refractive index to be the square root of permittivity. And now what? Now you had an incoming electromagnetic wave that is basically coming in with certain wave vector, which is basically the incident wave vector. And it is hitting this interface, and then we draw the normal to the interface with the incident angle, which is theta I, and then there is a transmitted angle, which is theta transmitted, and the transmitted wave vector is k transmitted. So this is the transmitted wave vector. And then there is a reflected part, which is basically theta r, and then there is a reflected wave vector of the electromagnetic wave. So when we are talking about a situation like this, we are talking about the oblique incidence, which is slightly more involved than the normal incidence. In the normal incidence, the electromagnetic waves comes like this. Okay, so you no longer have to deal with all of these scenarios. That is a more simplistic scenario, and that comes because of it. In the normal incidence case, the theta I becomes equivalent to 0, and you have the normal incidence. Okay, and essentially what you do is that you divide this into two components. You divide the incident wave vector into two components. Let's say the coordinate system is something like this is the z direction and this is the x direction, and the y direction is going something like inside it. It's showing the thickness or the width of the slab. So this is the z is basically the thickness of the slab direction, and x is basically the spatial in plane or the width of this particular slab. Y will be the length of this particular slab. So we have the KIZ component, and then we have KIX component. Similarly, here we have KRX component, and then we have KRZ component. So KR is here, KRZ component, and here again we have KRZ component. We have this is KTZ component and KTX component. So essentially you see that these wave vectors are basically showing the wave vectors of the oscillation of the electric field right here. And when you notice it, you notice that for incoming wave, the wave vector looks something like this. For the transmitted wave, it's also like this. For the reflected wave, the x1 is okay in the same direction, but the z1 flips. It goes in the opposite direction. So essentially, the wave vector goes in the opposite direction for the z component of this of the wave vector. Now what? Why is it going to be necessary? Because it is going to be necessary in order to understand how the electromagnetic wave behaves with the different media. So let's say you are given a scenario wherein you need to basically find these transmitted electromagnetic wave components, reflected components, what information you need, and how can you find them. Essentially, you can find them by just resolving the vector. So these are just this is just vector calculus. Okay, and you can write the kix. So if this is angle, let's say we're talking about theta t. Let's say we're talking about this. So you have kt, you have theta transmitted angle here, you have ktx, this is ktz. Then your ktx is essentially magnitude kt sine of theta d, and this magnitude kt is basically this thing. So we're resolving it into two components. So ktz will be magnitude kt cos theta d, and theta d you can obtain. Okay, and kt also you can obtain. The magnitude kt will be equivalent to omega under root of mu epsilon, but this is of the slab because it's inside the slab, the transmitted. It depends upon where the transmitted wave is. If it's in the air, then you use the values of the air. If it's inside the slab, then you have to use the values of the slab itself. And okay, sorry. And what happens now? Essentially, you can find KT, KR. You can similarly resolve this reflected component. You can resolve the incident component, and finally, you can write these in terms of the vectors. So you obtain the Ki vector, you obtain the K transmitted vector, you obtain the K reflected vector. This is going to give you the information about different constituents in the vector. Let's say you obtain KT something like 2x cap plus 6z cap. What it is going to show you, it's sort of a vector that is moving in xz direction because it's at an angle, which is basically theta transmitted angle. That will be tan inverse of 6 divided by 2. Okay, and then its magnitude will be under root of 2 square plus 6 square, which will be under root of 4 plus 36, which will be under root of 40, and this is basically magnitude of kt. So similarly for all of the components you can find. And now if you need to find the transmission coefficient, let's say how much of the electromagnetic wave is transmitted, again how you can find the transmission coefficient is to look at the electric field amplitude which is transmitted divided by the field amplitude that was incident. And this comes out to be equivalent to twice eta t cos of theta incident divided by eta t cos of theta incident plus eta I cos of theta transmitted. So this is exactly how you can obtain the transmission coefficient, provided you know eta t, which is basically the impedance faced. So the eta t can be obtained, which is basically the impedance faced by the electromagnetic wave, and the impedance faced is basically the difference of the refractive index divided by the sum of the refractive index. Now, essentially, this is basically the reflection coefficient. Sorry, so this is basically the reflection coefficient, not the essentially the intrinsic impedance. The intrinsic impedance can be found according to the rules that we have studied in the previous cases as well. So you have basically the the impedance in the transmitted media and the impedance in the incident media, where the medium where the basically, just give me a moment. Hold on. Okay, so now if you if you want to find one of these, you can solve for it, and accordingly, if you want to find the magnetic field component in the transmitted waves also, then you can find it using its wave vector, transmitted electric field divided by eta transmitted. So how much is basically going in? So this is basically controls the direction, this controls the amplitude, and this controls how much is basically going inside it. Okay, so now this was about week 4, what we did in week 4. And then we moved into week 5. Week 5. And in week 5, what we studied or what we did is again sort of electromagnetic wave interaction with the slabs. We talked about glass air interface, and then we talked about the electromagnetic waves in guided medium. That means you had a waveguide, an electromagnetic wave propagating like this. Let's say you have the strip electromagnetic wave propagating in this direction, and you talked about TE or TM mode basically being propagated inside this waveguides. Okay, and what else you talked about was that if you have a interface like this, where this is refractive index N2, this is refractive index N1, and if your electromagnetic wave is coming like this from the N1 refractive index, let's say this is a glass and this is air, it will hit the interface, then there'll be decaying part, which is basically called an evanescent mode. It's called as evanescent decay. It rapidly decays outside the zone, and it goes up to the depth, which is basically called as, it can be also called as skin depth or a penetration depth or a tunneling depth, whatever. I mean, the name doesn't matter. And then it reflects to the other part of it, and essentially you can find how much of it goes out of the medium. So this depth, which is let's say x naught. How you can find it is basically using the concept of absorption coefficient. You can have absorption coefficient or what you call as attenuation coefficient also. So you can write it in terms of alpha to be equivalent to omega over c n1 sine theta incident. So the essential evidence is that if this electromagnetic wave hits with the angle which is equivalent to the critical angle, then it is going to go under total internal reflection, but there'll be still this decaying part outside the medium. Okay, if you find the attenuation coefficient, it will be in units of per meters. Then what you're going to do, you're going to find the intensity at which you're going to find the distance x naught at which the intensity drops to initial intensity divided by 2, and when you see that, you get e to the power minus alpha x naught drops to 1 by 2. That means I equals to I naught e to the power minus alpha x is basically comes from the exponential decay of the wave outside the medium, and if I drops to I naught divided by 2, that means this becomes e to the power minus alpha x equals to 1 by 2. So you solve this, you're going to get x naught from here. So this is going to give you penetration or leakage, or how much is the leakage of the electromagnetic wave or the evanescent decay. Okay, and most of the time it's very small. It also happens in case of if you have a metals, if you have a metal which is a sort of a perfect conductor, so you have a lot of electrons here, a sea of electrons, a huge concentration of electrons that almost acts like a these are free electrons, and then you have an incoming electromagnetic wave. Essentially, when it hits the metal, it decays exponentially, and it gets it's this is a small decay part, but most of it gets reflected essentially. Okay, so most of it gets reflected. That's why metals appear to be shiny, so on and so forth, because they are highly reflective. But it also depends upon wavelength, or it depends upon essentially the frequency we're talking about. So this depth also is it's also the evanescent mode leaking into it, and this is called as skin depth in the metal case, and it can be also similarly found in this fashion. It again depends upon the concentration of electrons in the metal, the permittivity of the metal, and the other parameters of the of this particular metal that you are talking about. So basically, these electrons, they are shielding the electromagnetic waves, and as such, they cannot penetrate deeper to the metallic system. But now there's a scenario that if, let's say, this metallic thickness was L1 and it was much greater than the let's say this X naught skin depth, then you're not going to see any effect because it's going to decay close to the surface of the metal. But what if you make a metal thin enough? What if you make a metallic sheet thin enough that the length approaches the order of skin depth? Then your electromagnetic wave is going to come and it's going to leak and it's going to appear on the other side. So there are different scenarios that basically happens when the evanescent mode basically leaks, and it can couple to the others on the other side, and depends upon whatever you have on the other side. It can be a semiconductor, it can be another metallic strip. So then there we talk about something called as plasmons. We talk about the plasma interaction with the metal, so on and so forth. We don't have to go into this detail, but this scenario can happen if you make the thickness small enough that it becomes of the order of penetration depth, then your essentially electromagnetic wave can leak through it. And this is usually done using nanostructures. If you make it thin enough, let's say you make it of the order of 10 nanometer, you deposit a metallic strip of the order of 10 nanometers, then your electromagnetic wave can basically go through it. It can go through it. Okay. But if it is of the order of 100 nanometers, the thickness, then your essentially electromagnetic wave is going to leak. It's going to decay, but most of the electromagnetic wave will reflect. Okay, and that is what we basically saw, and we tried to infer or understand it from the electron's perspective, how the electron tunnels is essentially similar. If you have electrons, this is a potential barrier felt by the electron. Let's say this is a potential barrier, and let's say there's a negative charge here, a negative ion present here, and the electron is trying to move like this, then electron will face a barrier something like this. So it essentially looks like a barrier, which is basically something like this, the potential barrier. Okay, but then electron has two options. Either it can go over the barrier or it can tunnel through the barrier because it's acting like a wave. So the electron wave comes in, it tunnels, the electron wave comes in, it tunnels at this point and it appears on the other side. That is essentially the same thing. And it means if you now bring in more ions, you're essentially increasing the depth of the potential felt by the electron. So now you have a bigger barrier, a larger barrier. Now the electron wave is coming, it's decaying, but it's not appearing on the other side. There will be no wave on the other side. Most of it's getting then reflected, and you no longer have the tunneling process. Okay, so that comes because you solve the Schrodinger equation here, you solve the Schrodinger equation here, you solve the Schrodinger equation here. You combine the three Schrodinger equations, you solve it for the incoming wave vector of the electron, the reflected wave vector of the electron, and the transmitted wave vector of the electron. It's the same scenario because you're talking about the electrons as the waves. Okay. Now, what else did we study in where are we? Week 5 of this course was again the step refractive index. You talked about if you have a refractive index gradient, something like if you have a material system of, let's say, a waveguide which looks something like this, wherein this is the waveguide of refractive index of material N1, this is the refractive index N2, this is the refractive index N1 again. So you have a refractive index gradient like this. This is N1 refractive index, N2, N3. So when your electromagnetic wave will come, it will naturally couple to medium with higher refractive index here. So you will have modes here. So your modes are basically the solutions of Maxwell's equation, and you solve the Maxwell equation, you get the modes inside this to be something like this is N1 mode, N2 mode, N3 mode, similarly so on and so forth. These are basically the different spatial variations of the electric field as well as the magnetic field. And as per their spatial distribution, you talk about whether they are TE mode, whether they are TM modes, whether they are TEM modes, whether they are TE010, whether TE11, depending upon how they are spatially distributed. So essentially, it's a function of x, y. It's a function of x and y, and they are propagating in certain z directions. Okay, so essentially, E of x, y is basically propagating in the z direction. Okay, and then we move to week 6. Week 6. So it's a sort of a it will be a good revision if you just go through everything what we have studied till now, so that you can at least have a rough overview of this what this course basically offers. And in week 6, you talked about electromagnetic waves. So you talked about the modes. Continue talking about the TE modes, TM modes. We talked about the radiation pattern, which is essential in case of the antennas. So basically you went into wireless communication domain. And when you talked about the wireless communication systems, what you did is basically you talked about also you talked about the modes in the waveguides. You talked about something called as cutoff frequencies, cutoff wavelengths. Okay, and you said that if your frequency is less than cutoff frequency or the wavelength is greater than cutoff frequency, your waves will not propagate through the waveguide. And what it essentially meant was that if your waveguide is like this, and this is, let's say, some sort of a width of this waveguide, and if your wavelength becomes greater than this width, or essentially it basically goes out of this particular width, then you no longer have the propagation of that electromagnetic wave through it. Okay, so that's why if let's say we call this as lambda g, or we this is a, and we call the wavelength inside it as lambda g. If lambda g becomes greater than critical wavelength, then your wave is no longer being supported by the waveguide. And how you find the critical wavelength is 2 times the for the TE mode, for the the first mode, the dominant mode, which is basically the dominant mode of the electromagnetic wave inside the waveguide. How you find for it? The critical wavelength is 2 times the thickness of it. Okay, and how you find a wavelength? You find it by speed of light over frequency. How you find the wavelength through the waveguide will be wavelength divided by under root of 1 minus lambda over lambda c square. This is exactly the wavelength through the waveguide. And if you want, you have to calculate this, you have to calculate this, and then you have to calculate this, and you compare these 3 quantities in order to understand whether your wavelength is greater than critical wavelength or it's less than wavelength. But you always need to compare, just to make sure, you always need to compare the cutoff wavelength with the wavelength inside the waveguide and not this wavelength, because this is the wavelength in space, free space, out of the waveguide. So this is in free space. This wavelength you need to compare it with. That means inside the waveguide. So you need to compare lambda c with lambda g and not with lambda. So this is essential. Okay. And now what else did we study? We studied about the impedance of the waveguides. Again, we studied there's the same similar factor that comes that the impedance faced by the TE mode will be intrinsic impedance, characteristic impedance. This is basically the characteristic impedance of free space, which is around 377 ohms, divided by the same factor, which is 1 minus cutoff frequency divided by frequency square. Okay, and this cutoff frequency is essentially C over 2 pi under root of m pi over a square plus n pi over b square. So this is the cutoff frequency that we are talking about. So essentially it depends upon, this is some sort of a wave vector in x direction, and this is the wave vector in y direction. So it essentially is fc is c over 2 pi under root of kx square plus ky square. Because you have a waveguide, this will be the kx, let's say, the wave vector in this direction, and then this will be the k, let's say, ky direction. This is basically the z direction, propagation direction. So this will be the ky direction. It's difficult to show it like this because the three-dimensional spatial uh, spread of the spread of this particular electromagnetic wave. So essentially, your mode will look basically, if you look from the top end of the waveguide, you're gonna see something like, if for the first TE dominant mode, you're gonna have a Gaussian, but if you look from the top end, it will look something like this, where this is basically the kx, this is basically ky, okay, and this packet is moving all together in the z direction. This is the top view. If you look at those how those modes are propagating, and you will have a distribution like this if you draw it in a color, and you will have a distribution like this in y direction also, and accordingly you will have a Gaussian sort of a packet moving through it. Okay, so now again we talked about intrinsic impedance. We talked about the impedance inside the waveguide for the dominant mode. We again talk about attenuation coefficient. Attenuation coefficient for this dominant mode inside the waveguide, it will be exactly, why this timing is showing that it ends in 15 minutes. Okay, anyways, I'm gonna create a new meeting. This will be again modified by this particular term, which is fc divided by f square minus 1. So everything that is basically modified inside the waveguide is your wavelength inside the guided media is basically the wavelength in free space divided by this factor, which is 1 minus lambda over lambda c square. Your attenuation coefficient is modified by multiplying the frequency factor. Your intrinsic impedance, your impedance is modified by this factor again. So everything is basically modified by this particular factor. Okay. Then you talked about a Hertzian dipole antenna. You talked about a Hertzian dipole antenna. And in here you talked about, let's say you have an antenna which is connected to an oscillating source, and it's going to emit the electromagnetic waves. And we talked about how this functionality behaves. And then here you talked about a near field and a far field regions. Okay. And you talked about near field and far field, but the point is based on what? So based on the frequencies, obviously, the frequency, the wavelengths. Okay. And then you talked about the the directive gain and directionality of the antenna. So essentially, if you have a dipole antenna, its direction pattern is going to look something like this. So it's going to propagate most of the electromagnetic wave through this direction, and you need to consider essentially a coordinate system which exactly looks like this. So you have a antenna at this point, and this is the R direction. So this is the theta, or you can also consider this as theta, and then this is the phi direction or angle. So you have a coordinate system as r, theta, phi. So if your theta becomes like this, essentially you can also, it depends upon what coordinate system you're using. So you can use this as theta. If your theta becomes pi by 2, so you can have a maximum transmission. So these transmission lobes are basically determining the region where the maximum of the field is basically going. Okay. Then what we talked about is that for the near field and far field conditions, we can essentially write the magnetic field if you have a because if you have a current carrying wire, and if we want to find the magnetic field at a point, this point you always consider it in a far field region. But if you bring this point very close, so you have a near field condition. And in that condition, you can basically encompass both of these conditions in the Ampere circuital law, as you can write the magnetic field at point P as minus phi cap, which is basically the directional vector, I naught dl. I naught is the current it's carrying, dl is the small length element, divided by 4 pi e to the power minus j beta r beta square 1 over j beta r plus 1 over j beta r square. So this is essentially it. So this takes into consideration both near field and far field conditions. Okay, and if you only have a far field condition, you would essentially this is square of this. If you only have a far field condition, you essentially have only this term. If you have a near field condition, you only have this term. So that is what the term you basically studied in the high schools also. And accordingly, if you are given the questions where you need to find the near field and far field conditions, you can find these particular terms accordingly. Now what else? And one more thing, that if you are given the directivity, which is basically averaging over the entire volume, so your directivity in theta comma phi direction will be the u theta of which is basically the radiation intensity. U theta phi is basically the radiation intensity averaged over the entire volume. It's averaged over the volume. So U is basically the resistance square into average power, and average power you can write in terms of the Poynting vector, which is half of real part of E cross H conjugate. Okay, or you can also write it in terms of E theta H phi, as simple as that. And if you are given directivity and you have to find the uh, this is essentially not the directivity. You can find the directivity in terms of the decibels by taking the log of this quantity, log to the 10 log to the base 10 of maximum of GD theta comma phi. So this is exactly the directivity in decibels, decibel scale. Okay, so for the near field condition, when you talk about the near field condition, you have the R is much less than lambda over 2 pi. For the far field, you have the R much greater than lambda over 2 pi. Remember? And accordingly, if you are given the wavelength, you can understand how much distance your antenna should be from the particular object, so that we consider it as a near field from the point where we are measuring, so that we consider it as a near field and a far field. Okay, what else? What else did we study is how the electromagnetic wave behaves uh, inside the different media. Let's say in free space, let's say in water, what will be the radiated electromagnetic waves? We discussed that in detail, I guess, in week 6 of the course. Then we moved into week 7. Week 7. And in week 7, we talked about linear antenna, we talked about Friis transmission equation, the array factor, we talked about multiple antennas. And essentially the concept was that if you are given a sort of a scenario where there's a transmitter, there's a receiver, then essentially your received power is a function of, which is power received is a function of transmitted power, transmitted gain, received gain, divided by lambda over 4 pi r square. So this is something called as Friis equation. And you found out that the received power is basically proportional to the cross-sectional area of transmission antenna, cross-sectional area of the received antenna, which makes sense. Okay. So and and this G, which is basically the gain of the antenna, is proportional to 4 pi, the cross-section area of the antenna divided by lambda square. Similarly for this is for the transmission, similarly for the receiving antenna. Then what you found out is this was mostly about the week 7. Then you had a linear element, the antenna, where you had the different elements of the antenna that are emitting the electromagnetic waves. Again, I have discussed this in very detail, which you can find that each electromagnetic wave is going to interfere. It's going to make the interference pattern. So there will be certain regions with constructive and destructive interference. And then you talked about here something called as an array factor. So what this array factor was, you found it to be equivalent to cos of half of kd cos phi sine theta plus alpha. And this d is the distance between the two elements. Okay. And it is emitting at certain theta, obviously. And then this k is basically 2 pi over the wavelength. The d is basically the spacing between the two elements. So you can find this array factor, which is basically comes out to be a number. And what it tells you essentially, when you obtain the array factor, you obtain the array factor for different phi directions. And then you draw a figure, which is basically you vary the phi and you obtain the array factor. You obtain an array factor something like this, depending upon how you get the values, which is basically XY mapping. Okay, you can get an array factor something like a point. You can get array factor in a different form. So it basically shows you the distribution of this. Okay, so now what? Then what did we study? We Our meeting is going to end in 4 minutes. I think I need to then create a different meeting. Let me create a different meeting. And we went into, this was week 7, then we went into week 8, which was more recently on last Saturday. And here you talked about optics more, which was lasers, talked about coherence, we talked about laser pulses, transforms, diffraction, and interference. And this is like more recent one, so there's no need to just revise it entirely again. But essentially the concept here was to go from a time to frequency domain or from a real space to inverse space domain to understand their diffraction patterns using the Fourier transform image. And in here you talked about basically the Gaussian beam basically propagating with certain beam waist, and then there is a length called as Rayleigh length, which essentially takes into consideration at what point the amplitude of this particular Gaussian beam drops, and this Rayleigh range was pi beam waist square divided by lambda. So you can find the Rayleigh range. And you also talked about the break point in wireless channels. What was this breakpoint? At this breakpoint, the power behavior basically changed. So the power behavior changed, and that means you have a transmitter and transmission antenna, reflection antenna, you have the ground. So one of the wave go like this, the other part goes like here. So there's a phase change at this particular place. It can interfere constructively or destructively with the incoming waves, with the initial propagating waves. And accordingly, your power up to this point, you saw that the power varies as 1 over d square, but after this, the power is going to vary as 1 over d to the power 4. So you have a minus 40 dB per decade of loss after this. Before this, it was minus 20 dB per decade. So it goes from minus 20 dB per decade to minus 40 dB per decade change. So essentially, there is a change of the slope of the power at this particular point, which is basically called as a breakpoint. Okay, then you talked about diffraction. You talked about Fraunhofer diffraction patterns, which is essentially the Fourier transform of Fourier transform in from real space to the K space. And yes, and then you also talked about that if you have different slits, you shine it with electromagnetic wave, how the different diffraction patterns are gonna form. It's essentially going to be again the Fourier transforms. And then we talked about the rectangular to sync transforms, so on and so forth, how the interplay is going to take place. I think this is more recent. You can just go to week 8 and you can just see all of these phenomena, all of these in my lecture. It'll be great if you can do it. And then finally, yes, then finally we were done with this lecture because this is more recent. I'm not going to discuss details about it. And yes, let me check. Yes. So this was about it. And essentially we are done with this course. So it was a really nice experience for me also. I hope you guys were watching the videos on the YouTube because I wasn't getting much I should say I wasn't getting any students online, maybe one or two at max. But I hope that you guys were watching it over the YouTube and enjoying it. And I'm not going to say that if you enjoy, just like and subscribe, but uh, because this is I'm doing because I'm liking it. I'm not doing it for the sake of getting the fame or something like this. I mean, it's beyond that. Whenever you do something for the society, it should be beyond the recognition and the fame, and that's what most of the scientists do. We barely remember any of the scientists in our era who have done a tremendous job to make our lives easier, also to make our lives hectic because there are a lot of situations going around. But it's fine. Like this, how the world has been since ages, and so I hope I could at least, uh, I should say, motivate you to pursue the career in research because these fields are very active. So if you talk about from the research point of view, which I'm going to close with this particular thing. So from the research point of view, this is always essential because the today's research is not that somebody is doing research in electrical engineering or somebody is doing research in mechanical engineering or chemical engineering or civil engineering or computer science. This was the old-fashioned sort of concept. Today it's interdisciplinary. And when you talk about interdisciplinary, you are essentially talking about using the lot of domains together. Okay. And that means all of these things come into single picture. So if I talk about myself, what I am working on and which domains I use often, it can be categorized into, let's say, if I could divide this circle into different sectors, and if I count the number of fields I use day to day in my research. So my research, let's say if I talk about my research, it's an experimental research on electron phonon dynamics and electron phonon interactions in semiconductors. Okay, so essentially you can understand from this what basically we are doing. We are, oops, we are we are essentially studying electronics. Electronics, let me try it like this. So I am studying electronics from the perspective of semiconductors. That means we're studying solid state devices, solid state physics, and we're studying phononics. That means we are also dealing with the thermodynamics aspect, and we are also dealing with the waves because we are treating also the electrons as waves. We're treating the phonons as waves, sometimes as particles also. So there's a wave mechanics picture coming into this. We are doing the experiments with optical equipments. That means we are using lasers. We are using all sorts of lasers. So we are going into the optical domains as well. And when we are going with the optical domains, we are talking about electromagnetic waves interaction with the matter. So we are basically talking about light matter interaction also. Okay. And we are doing everything at a nanoscale. So we are talking about essentially nanotechnology, how the systems behave at a nanoscale. And the master of it is basically when we go into this region, you're essentially talking about quantum mechanics. So that means you're dealing with certain atoms. You try to understand how different atoms behave and how their electrons behave in the different atoms. What are their electrostatic potentials? How the phonons behave? How you can find the dispersions? How you can find the phonon dispersion, electron dispersion? Then we talk about the transport regime, which is basically uh, it's essentially how the phonon is transporting inside the system, how the electron is transporting inside the system. We solve certain, let's say, transport equations, it can be a Boltzmann transport equation, it can be a Wigner transport equation, a general form basically. So, so this is just a brief overview of what we exactly do in the research today's world. So you have to deal with these things. And essentially, we can also make one more sector here, basically. If we make one another sector here, we are also dealing with, let's say, for example, in order to understand all of this, we're simulating it also. And when you do the simulation, you have to understand you have to write a code, you have to play with the code, or you have to essentially go into the computer science aspect of it because you are doing everything on the computers. And then you have to deal with supercomputers because you are simulating it on the clusters. This is such a huge system of atoms which cannot simulate on your normal computers. You have to use the supercomputers. So this is the essential picture in today's world that we basically deal with. That's why having the essential or the in-depth understanding of semiconductors, having the in-depth understanding of electromagnetic wave behavior with the system, about the thermodynamics, about the waves particularly. I mean, the wave phenomena is essential. If you can understand the wave phenomena, you have understood most of the things in physics. About the quantum mechanics, about the light matter interaction, about how the nanoscale behavior does, about how the transport happens at a nanoscale, quantum transport, and all of this goes together. And if you are lacking in any of the field, then you basically get stuck. You cannot move forward. Always have to go back to the basics, and then you don't have enough time to go to the basics. Okay, I always tell my students that if you are at class 10th, you are at 11th, you are at 12th, then you do the bachelor's, and then you go to the, let's say, master's, and then you go to the PhD program. But you do well here, but if you lack something here, you have not understood concepts at this place, you're gonna maybe do well during the first year, second year, but third year maybe you will do well in your bachelor's. As you go to your master's, you can also do well, but as you go to the PhD, you will lack certain understanding of the concepts because it again boils down to the concepts that you study in 11th and 12th. Okay, let me tell you a brief example. You might have studied about simple harmonic motion in class 11, which is basically, let's say, a spring mass system, a simple spring mass system with spring constant K and mass M, and this displaced by X. So you have the potential energy profile as half of m omega square x square. Okay, so this is the potential energy profile of spring mass system. If you understood the phenomena that is basically happening with the spring mass system, or even the pendulum, that is basically a hanging pendulum of mass m. So there is this is a massless pendulum, but there is tension. Let's say that the tension in the pendulum is some value t. But essentially, what it basically happens, there's a simple harmonic motion again. And if you have not understood this problem, if you have not gone through the maths of it, you're gonna go into the field here and you're gonna talk about, let's say, phonons, or even if you talk about the electrons. And whenever you understand these things, you are going to understand in terms of simple harmonic motion always. It's gonna boil down to these basics. It's just a one example. It's gonna boil down always to these basics. Similarly, if you're doing PhD, you are dealing with a lot of signal processing. You're dealing with the signals, you have to process them, you are dealing with the Fourier transforms, you are dealing with a lot of transforms, and it boils down back again how well you have studied these things in your bachelor's. Because all of these courses are in bachelor's. So that's why those courses are necessary. I'm not telling you to entirely spend your life on the courses, but if you're doing it, do it with enthusiasm. Just not do it for the sake of qualifying the examination. That's my whole point. So that all boils down to how well you have done in your previous classes. That is what is going to basically make you successful at this particular level. And you see that most of those people are successful who have at least done well in these classes. I'm not talking about well in terms of getting a good GPA. Obviously, getting good GPA is, I mean, absolutely fine. That is the first thing that people see in your CV even. But conceptual understanding is important. You have to get the conceptual understanding at these levels in order to get into this particular research domain. So that's it from my side for now. I hope I could give you at least some flavor of this particular course. And you can go through this lecture, and if you have any doubt, you can always reach me. And if you want to reach me, my email is, I'm going to give you my personal email, which is shazanbutt.iitb@gmail.com. If you want to, if this is my personal email. If you have some other queries, maybe professional queries, then I'm gonna give you my office mail as well, which is bhat, bhat@pdi-berlin.de. This is dash and not underscore. So these are the mails you can just always contact me, and I wish you very good luck for the upcoming courses and upcoming for your future. Thank you. See you guys soon, maybe in the next course.